Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020, and the title of this lecture is The Wave Equation and Fourier. So, the wave equation, here's the model. Consider a string of length L, capital L, such as a guitar string that is stretched tightly between 2 points on the x-axis, and let's just call them x equals 0 and x equal capital L. When the string starts to vibrate, we assume that the motion takes place in a plane, and that's going to be the XU plane, in such a manner that each point on the string moves in a direction that is perpendicular to the x-axis, and these are called transverse vibrations. We'll look at a picture of this in a minute. We're going to let U of xt denote the vertical displacement of any point on the string measured from the x-axis for t greater than 0. And we further make a whole bunch of assumptions. The string is perfectly flexible, it is homogeneous, that means its mass per unit length, rho, is a constant. The displacements are small in comparison to the length of the spring. The slope of the spring is small at all points. The tension T acts tangent to the string, and its magnitude T is the same at all points. This is a vector T, and so tension is a force. The tension is large compared to with the force of gravity, so we're going to be basically ignoring the force of gravity, and no other external forces act on the string. Here's the picture that we were talking about. So this is the U-axis, this is the x-axis, and U of xt is the displacement perpendicular to the x-axis of that point. And we're going to be focusing on a little element over here called delta S, where S is this blue part right here, and that is the curved part of the string, and we're going from x to x plus delta x. So that's what we have in those pictures, and here we have a blown up version of that same picture. Okay, so in the B picture, the tensions T1 and T2 are tangent to the ends of the curve on this interval, and that was one of our assumptions. So we have the capital T1 and capital T2 down here. Those are vectors. Now for small values of theta 1 and theta 2, the net vertical force is the difference between the two of these. So you see, we're talking about the vertical force. So this vector has a horizontal component, but also a vertical component going up. This vector has a component going down and a horizontal component going the other way. We're only concerned about the vertical. So what we say is that that is t sine theta 2 minus t sine theta 1, where that's the magnitude and the theta tells us the direction. Now that's approximately equal to t times tangent of theta 2 minus t times tangent of theta 1, because when you're close to 0, the sine theta is very close to the tangent of theta. You may want to think about that for a while, but that definitely is true. And the tangent really is the rise over the run, which is the slope, and the slope is the partial derivative in the x direction. So at theta 2, it is the partial derivative with respect to x of u of x plus delta x t minus, and this is at the original point, u sub x, the partial with respect to x, at xt. And down here, they're reminding you that that's the definition of the partial derivative that we're going to be using in just a minute. I think actually that's a little bit premature, them telling you that. But anyway, what we're going to do is, and then we had an assumption that the magnitude of the force is the same, the tension is the same everywhere on the string. Now, this is going to be m, the mass, because rho is mass per unit length. That's the length of the arc length, and that's approximately equal to delta x, because it's a very small interval. So if we apply Newton's second law, this is the force, the net force, then is equal to rho delta x, and that is Now where we are going to be doing this then is this mass times acceleration, which is the second derivative with respect to t. So it's the second partial with respect to t. Divide both sides by delta x, and now we're going to take the limit as delta x goes to 0. This is where they should have had that footnote, because when I take the limit of this, that's just going to be another partial derivative, so that is the second partial derivative. And I look at what I have here, and I'm going to have rho over t is that. So you see I end up with, and I'm going to call this constant a squared because it is positive. So I get a squared. Actually, the a squared is going to be the reciprocal of that. I put that on the other side. And so this is a squared. This is the second partial of u with respect to x is equal to the second partial of u with respect to t. Now notice this is very different than what we had with the heat equation, because the heat equation was the first derivative with respect to t is equal to this second partial derivative with respect to u. Okay, and we also now have some initial conditions and some boundary conditions. So the initial conditions are, we know the initial shape of the spring, and we call that f of x. And we also know the velocity at time t equals 0 everywhere on that string for every place between those points. We also have some boundary conditions. You see, these are initial conditions because these are when t is equal to 0. But here we're going to have places where these things are happening. So for any value of t at the point x equals 0, and at the point x equal L, we're saying they're nailed down, and this is just 0. Now there's all kinds of other boundary conditions you can do, but we're just going to focus on these. So our problem is, what we want to do is solve this equation. There are our boundary conditions, there are our initial conditions. Now when we go to solve this, you'll notice that many elements of the solution look similar to what we did before. First of all, what we're going to do is we are going to separate the variables. So we're going to assume that u of xt is equal to capital F of x times capital T of t. And whenever we separate the variables, we will get this relationship. Now notice that this is going to be, these are equal to minus lambda. That means this has to be a constant. So we get two first order differential equations, this one that's called 4 and this one that's called 5. Now 4 is exactly the one we had in the heat equation. So when we solve this one, we have three possibilities, and we go through those possibilities, but the only one that leads to a non-trivial solution is when lambda is equal to alpha squared. So that means the general solution of this is going to be x is equal to c1 cosine alpha x plus c2 sine alpha x, and the boundary conditions tell us that alpha, the only values of alpha that we can have a solution are going to be n pi over L, and that means that these eigen values are going to be n squared pi squared over L squared just as before, and the solution is going to be a constant times this eigen function. Now the t works similarly, except it is a little bit different because what we're going to get here is it's a similar thing, except it's a little bit different. The C3s and C4s are different, and we are going to call now, whenever we multiply those things together, an and bn, but you see we get a similar kind of thing for the t this time. We don't get a negative exponential like we did in the heat equation. So now our solutions are a function of n, and they're going to be capital AN cosine of this plus capital BN sine this. That's the t of t, and this is the x of t that we get. Now we don't know what AN and BN are, so we have to think about that, but this is the solution that we have once we figure out what are AN and what are BN. But when we take the initial condition here, t equals 0, and this initial condition, that tells us that f of x is equal to the infinite sum of an sine n pi L over x. That tells me that what I have is a Fourier series, and this is the Fourier sine series. We already solved that, so an is equal to this integral. So that's what an is. To solve for bn, we differentiate the formula that we have, and we get this expression. Again, you should check all these derivatives, but that's what we get. We plug in t equals 0. Now t equals 0 tells me the cosine is going to be 1 and the sine is going to be 0, so this ends up being g of x is equal to the summation. Now we get a little bit different kind of configuration here for this, but you see that this is really a Fourier series for g of x, and so these coefficients with the n pi a over L is going to be equal to these Fourier coefficients. And when I solve for bn, I get this. So now we have solved the wave equation. And notice that Fourier series came in again big time in our solution. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.